Hi guys, can I get a sound check?
Sure.
You're good.
Okay, thanks guys. Let's see, lecture slide, spring. See, everybody's shy, huh? Nobody wants to turn on their videos? Come on. Come on. Who dares? Being recorded, continue. I'm the only brave one, huh?
Depends if there's extra credit in there.
Uh-huh. Good answer. Okay. All right, guys. So let's see. I was gonna just give you guys an example of what a chip looks like. And you know, at each class, I try to have some kind of like a make-believe scenario that goes through the whole class. Like I don't know if you guys are familiar with NVIDIA, but you know they make gaming chips and other kinds of chips. So some of the students are familiar with them. So a couple other semesters ago, we did a situation where we were pretending like we were going to do an interview. We're preparing for an interview at NVIDIA, blah, blah, blah. And so it gave us a chance to look at different things, like look at what like the stock price of NVIDIA meant for the employees, or how to read a technical paper from NVIDIA so you're prepared for an interview, so on and so forth. So I think this semester I'm going to do the same thing with Qualcomm. It just happen to be another big semiconductor company. I don't know if you guys have heard of them, but they're really, really big in cell phones. So for example, all the iPhone 12 chips, all the 5G stuff is all Qualcomm. And my brother works there, so I thought it'd be, you know, how can I not do Qualcomm? So I thought I'd show you guys just as an example of what like a chip looks like. You know, what is it we're talking about? I'm just put a few slides together. One of their chips that they used to sell. I think it's kind of old now. It's a little bit older of a chip, and I used it because there was more material about it on the web. I just sort of put this stuff together. They call their most of their chips, they're called the Snapdragon 820, 830, 840, whatever. So this is about stuff about a chip that's a Snapdragon 820. So basically what that is, it's an older chip, about probably 2015 it came out. It had 2 billion transistors in a 14 nanometer process, which is already pretty advanced, even going back. And it shows you that companies like Qualcomm that are, you know, big semiconductor companies, they're always on the bleeding edge of processes. So even 5 years ago, they were using 14 nanometer processes. They're using 5 nanometer today. Okay, 2 gigahertz clock rate. I think if it was running flat out, it would do an 11 watt power consumption, but obviously there's a lot of power down modes in your cell phone. And my guess is they were charging less than $100 for it at the time. Just because I saw like a cell phone, I think it was a Chinese cell phone that was made with it around 2016. And that cell phone was like $300. It was a $300 cell phone. So this chip was probably $50. as part of that. We'll see how that, you know, typically how people come up with these kind of pricings. So it's about that kind of price. And basically you could just take this chip, add, you know, a sort of like a camera module. You'd add the microphone, you know, accelerometer, display, etc. around it. All of them would basically, all their outputs of all those devices would go into this chip, and then you'd get a cell phone. Okay, so this is what this is what the sort of this thing would look like at a board level. Okay, so I don't know, so it's pretty small chip. So this is the you know, this is that chip. Okay, and on this board, I don't know if you guys are all used to seeing printed circuit boards or whatever. You know, see them in the, so there's, you know, a couple of other smaller chips. I'm not sure what they do. These are all like capacitors, okay, for in support of this chip. And, you know, there's probably some analog components here and there. Okay, and we'll talk about all these. So what happens is, this is a package, and we'll also look at the different packaging options. So this is a piece of plastic. It's probably pretty small. Okay, what that the silicon chip is, it's inside that for mechanical support and having the pins out, etc. So the silicon chip itself looks like something like this. You know, they've done these drawings on top of it to show you what the circuit elements are doing. But for example, if you sort of, it's low resolution, I cut and pasted it. Even if it was high resolution, it wouldn't really make up much, because, you know, this is probably, I don't know, this is probably, you know, I don't know, like a couple of 100 million transistors, maybe more, maybe 500 million transistors. So you're not going to see individual transistors, but you see kind of blocks, just because of statistically certain blocks look a certain way. You can see there are all these different blocks here. And they put this, you know, they said this is a CPU. So this is, it's basically a piece of silicon that maybe is like a millimeter thick. And you guys saw the package. Maybe the package is, I'm trying to say, it's maybe a centimeter by a centimeter. So the chip sitting in there is probably like, I don't know, like 8 millimeters by 8 millimeters or something. So this is what it looks like physically, the chip. This is not to scale or anything. And from a block diagram, so what I mentioned was, that's the sort of this chip, and it's going to have, basically they designed it so, you know, that's what's useful about having 2 billion transistors to play with, is basically they have all the goodies to build a cell phone circa 2015, and probably not a real high-end cell phone, sort of more like a sort of a commodity cell phone. So this has all the interfaces you need. I don't know, it has, you know, HDMI, we're all familiar with that. Back then it had USB 2.0, USB, what's USB 2.0 ports, USB-C chip. Let's see, what else? This is like the CSI is the camera interface. This is the audio interface. There's stuff for, I think this is the cell phone stuff, and this is the Wi-Fi stuff. This is all the stuff that's outside the chip. But then basically, you know, basically the users, what they do is get all these components, put it in with this part, and sell it as a cell phone. You know, of course, make the case and all that good stuff. So another important point, which we're not going to really look at in this class, is that when you design a chip, so this is the Qualcomm chip, you know, for your customers to be able to use that chip, you need to have a lot of support to the customer. So for example, you know, there's a like incredible amount of documentation, different design tools that go into it. They have partners that, build the rest of this hardware, the cameras, the Wi-Fi chip, whatever you name it. So they have these guys that, they have examples of how it works with this. There's actually example designs, okay? Then they have software partners that, basically you can go to and, license different pieces of software from, and then you can build your own cell phone. So, when you're talking about a lot of the cell phone makers, I'm not talking about Apple or Samsung or whatever, talking about these companies sort of, it's mostly the Chinese market. I don't think we see a lot of cell phones here. Maybe we see the cell phones and the, like $200, $300 cell phones. It's not like everything is built in that company. They're pulling all this stuff together, putting a shell around it, and they have a distribution sales network, and that's what they do. Okay, so anyway, this is what a chip looks like. Okay, and what it does. Any questions about that, guys? It's just at a very high level. Just sort of, and then we're going to touch on a bunch of this stuff. Like one of the things we're going to talk about is why did they stop at only 2 billion transistor? Why not throw some more transistors in there to do some other stuff? So we'll see why you might want to limit how many transistors you put on. Okay, so now slide deck 1, I talked about a bunch of this stuff in our first class Tuesday. So I'm just gonna sort of real skim through it. This was a sort of a history of computers and when the transistor was invented, and integrated circuits, putting multiple transistors on a chip, using the first microprocessor. We talked about Moore's law, which is, is hugely important. It talks about every 18 months, you double the number of transistors on a chip, which means you're getting, it's just incredible growth of the number of transistors on a chip and what you can put in there, transistor counts going up. We talked about all this stuff. The other thing that is, we'll see later, is when you make your, by the way, all this class, you guys are probably, when you study transistors, you looked at MOS and bipolar transistors. Bipolar transistors are really only used in discrete, they're not components. So if you were going to build a board and you needed an external amplifier or analog to digital converter or something like that, you'd use bipolar transistor. Whenever you're talking about chips, almost all the time, I mean, probably all the time, they're MOS transistors, okay, in there. So it just turns out that, the reason people started making MOS transistors smaller and smaller every generation was to cram more of them on the chip to reduce the cost of the functionality of the chip. So imagine if you look at I don't know if I have a graph on the cost per transistor, but imagine if the number of transistors on a chip is going up exponentially. And the way silicon manufacturing works is you're paying for the cost of the silicon area, more or less. Okay, it does go up with more advanced processes, but you're mostly paying by area. So the more transistors you can cram into that given area, the less an individual transistor costs. Okay, so it was all about reducing the cost of that functionality by increasing the number of transistors in a chip. But the way MOS transistor physics works is, for a few different reasons, the smallest is sort of a general rule. The smaller you make the chip, the smaller you make the transistors, the faster those transistors can go and the faster your overall system can go. So not only was the number of transistors increasing significantly, but so was the clock rate with this Moore's law. And it wasn't going up as fast as the number of transistors per chip, but it was still going up significantly. Okay, so this was what was happening, but a couple of things started slowing down Moore's law, like we mentioned last time. First one was power consumption, because what happened was, as you started putting more and more stuff on a chip, the power consumption of these chips went up. And power consumption is not like digital signal processing or something like that you can like improve your algorithm or whatever. It doesn't really work that way. It's like a thermoelectric problem or thermal problem, mechanical problem. There's really kind of only so much power, so much heat you can move away from per square centimeter at a reasonable cost. You can do stuff like liquid cooling, not in your cell phone. Maybe if you've got a gamer machine or something like that, you could do liquid cooling. You could do, you can do, some people use, what is it? They use oil, etc. But all that stuff, it only is going to go so far. Just the power consumption was going up significantly. It is a big problem. And gives you an example of what would have happened if power would have gone up. So this is a plot of the different, generation of chips and the power density. So power per watts per centimeter squared. And if they had kept cramming more and more transistors in a chip, by now, the heat, the power density on a chip in your cell phone or PC would be the same as the nozzle of a rocket, which is completely like nonsensical. Everything is going to melt at that point. So basically what happened is, this flattened out. And so that's one of the reasons they stopped cramming. Moore's law is slowing down because it's harder to cram more transistors onto a chip. And, one of the things they did and they're doing to extend that is one of the nice things about CMOS technology, which is what we'll be studying. So CMOS logic. Okay. One of the things that was really nice about it is the operative word, is that it only burned power when it was doing something. Okay, so only burned power when active. So let's say you made a 8 processor core chip, only one of them was on, chugging along, doing the math, 7 of them were asleep. Only the one core microprocessor core would burn power. So that was kind of the good old days. And so what people would do is they have, these extensive power down modes and still cram a lot onto a chip, but be careful what's operating and not. Now, the problem now is that even you burn power and a significant amount of power even when your circuits are off. And we'll see that that's a artifact of making transistors, these MOS transistors, smaller. You start getting leakage currents that even when they're just off sitting there, they're burning power. Not a lot of power compared to when they're active, but still enough power. And when you're talking about billions and billions of transistors, it adds up to a lot. Okay, so power density, power was the first thing that started slowing down Moore's law, meaning that we're not getting this doubling every 18 or 24 months. Okay, so let's see, what else did I want to talk about? This stuff is talking about scaling. Okay, the next thing I wanted to talk about was this concept of design abstraction levels. So this is hard for you guys to see at this point, but it's incredibly important to the way design is done in the world. And this is using the example of chip design, but it's really in every kind of design. So let's talk about chip design. Okay, let's say you know that you're putting a system together. Okay, so this is a chip. You're putting this 2 billion. You're the guy in charge of putting this 2 billion transistor Qualcomm chip together. Okay, and then let's say it was like an army of really bright people like yourselves. There was 100 of you putting this chip together. Okay, and let's say everything hierarchically, everything was flat. You'd have to go worry about every single transistor. So if you were working at this level of abstraction, meaning that if you start worrying about every single transistor on that chip is 2 billion transistors, like your grandchildren's grandchildren would still be trying to put that chip together, even if there was 100 of you, even if there was 1,000 of you. Doesn't matter how many of you there were, how hard you worked, you just couldn't do it. Okay, so what happens is when we're talking about these abstraction levels. Okay, so what people do is they have different layers. So when you work at the circuit level, when you're designing a circuit, okay, you only worry about transistors and how that circuit gets used in a gate. Okay, you're not looking, if you're tasked with designing a circuit, you're not thinking about how does the circuit fit into a 2 billion transistor device. Okay, you're only interested in a level of abstraction, one level, maybe a couple levels above yours and a couple level below yours. Okay, now let's say you were putting together, you were a very senior guy, and on this Qualcomm chip that said, okay, you are in charge of the memory module. Okay, these chips, I think it said it had 2 giga bits of LDDR. Sorry, guys. Ah, sorry, guys. I should be putting my phone on. Oops. Okay. Sorry. Let me put my chip on. My phone on. Do not disturb. Sorry about that. Okay, so let's say you were in charge of this 2 gig memory, and then this is not like something you'd be doing by yourself. Again, you'd have like 50 guys working with you. Now you do have to worry about how this fits in your 2 billion transistor subsystem, because it's a major module in that. And then you'd also have to worry about how let's say you have sense amplifiers or decoders in your memory. You have to worry about those, but you're not going to be worried about how the individual circuits are designed in there, because that's not the level of abstraction you're working on. Okay, like you're just working on your level and a couple layers above and below yours. And that's how this is the only way chip design can work, just because the complexity of these. If you were designing analog, like say you were an analog designer, you were designing analog digital converter, 14 16-bit ADC converter, and let's say that whole chip had I don't know, maybe 1,000 2,000 transistors, maybe even 10,000 transistors. Okay, so discrete analog chip, you could probably, maybe with a couple of buddies or whatever, you could probably handle that chip by yourself end to end, have that focus. But when you're talking about multi-billion transistor digital chips, you can't do that. Okay, so there are so many levels of abstraction, and the really the sort of the what happens a lot with young engineers is they get stuck because they can't work at the level of abstraction that they're at. They start worrying about how a transistor works when they should be trying to work at a system level. The really good, experienced, and chip designers know how to sort of tune that in and out, how to make sure that they're safe even when they're living with a or designing with a higher lower level abstraction. So there's a lot. I'm not saying it's just a concept, it's a whole discipline of how you can do that, but this is very, very important in chip design. Okay, we're not really going to touch it in this class. The book talks about it, different levels of abstraction, etc. Might touch on it a little bit, but if you do go into chip design, you'll see this. First thing you'll see is a lot of it is how do you do the right sort of abstractions and all that kind of stuff. I think you'll see it in every area of engineering. If you're putting a plane together, the guy who's designing the plane isn't going to be focused on the exact workings of the engine, the jet engine that goes in there, like how some component in the jet engine works. That's the job of somebody who's really focused at that level of abstraction. Okay, so anyway, I just wanted to bring that up just because it's an important concept. Okay, with that, I'm going to leave that, and then we're going to move to slide deck 2. By the way, I've been, and I'm going to try to do this every night once we're done with the lecture. So I'm putting the recorded lecture on YouTube, and then the notes, I'm trying to put the PDF in before the class so you can annotate it or whatever. And then the link to the YouTube videos also goes there, although that goes on Blackboard for that unit. Okay, so we're talking about designing a chip. And, when you're, a lot of times when you're in school, designing something means just functionally making sure that it works, okay? But in the real world, functionally working is just the beginning step, okay? So the question is, what are the other things that are basically you can judge how well a design works? And by judge, I guess I mean judge, but it's not just that there's like they pin a medal on you because your design was good. The good design gets the entire market. So for example, if the power, you design a chip for a cell phone, and your competitor design a chip for your cell phone, and the power consumption of your chip is twice that of your competitor, even if it's 10% more than your competitor, he's going to get all the market and you're going to get zero. Okay, so you're going to go out of business. So the market judges you about how well you do, okay, in that particular case. Now, so these are the criterion for how you can judge the quality of a design. And in practice, whether you'll survive, your company, what you're trying to do will survive and thrive, or your competition is going to eat your lunch. Okay, so these are the major parameters. First one's cost. And that's a real world thing. So, and there's two components to cost, which is how much to design it. Okay, so let's say you're designing a chip. It's going to take you and, I don't know, 10 other people a year to actually design the chip. Well, like let's say each one of you cost the company $200,000 each times 10. So that's $2 million in just salaries. Okay, so this is referred to, we're going to go into deeper. This is called NRE, for non-recurring engineering cost. And this is not just in chip design, you'll hear about NRE all the time. So this is the upfront cost of designing this chip. Okay, so you're using expensive computer-aided design tools. It's all expenses. You're keeping the lights on. Um, you're paying for the mask set, as we'll see, to make the chip. So those are all non-recurring engineering. Okay, the second part of the cost is the cost per unit once you're in production. Okay, so it's going to cost you, silicon costs you something. The testing of that silicon costs you something. You got to package it. You're gonna have people supporting your customer, all those kind of things. So that's cost per unit. So that's has nothing to do with how much it costs you to design up front. It's just the ongoing cost. And those are like really they're treated from a financial accounting basis as two completely different things. They have two completely different meanings for your customers. Okay. So for example, let's say you were designing something for a cell phone product. Okay. Now, anything that gets designed into a cell phone, cell phones nobody sells 100,000 cell phones of a particular model a month. If you're selling a cell phone, you're selling like 10 million cell phones a month. Okay. So the but so the cost per unit there is very important, because if every item in your cell phone costs 50% more than the competitor, you're not going to be able to sell the cell phone. But so it's very important. The cost per unit is very important, but nobody cares about the non-recurring engineering cost, because even if it was $100 million, $200 million to design that part, you're selling so many parts that cost gets amortized. So it gets divided over the 200 million cell phones that you sell. So even if it costs you $200 million non-recurring engineering, it's only $1 per cell phone. It's nothing, right? But if the thing you designed, the cost per unit is $15 per unit instead of $10 per unit, you're going to have a problem. Okay, so we'll talk about that. It's a significant difference between vice versa. Like if you're designing a chip for a military program, let's say for a fighter jet, there's only going to be, or whatever, there's only going to be 1,000 of them ever made. So they don't care if that thing costs $10,000 per chip. That fighter jet already costs, I don't know what the heck fighter jets cost, $100 million. And so a $20,000 thing isn't going to break the bank. But usually the budget for the entire program is decided by Congress, and your piece is this much. And so it's all about, can you do it for that non-recurring engineering cost? Okay, so cost is one of the metrics. And we're going to, again, address all these things in the class. Second thing is reliability. Okay, so again, when you're in an academic environment, in the lab, even in grad school, just want to see something works. Either it works, you write down the results in your report, or you show it to your academic advisor, write your paper, good, you're done. Okay, you don't care about reliability. It just has to work in the lab, air-conditioned lab, nice power supply, good components, with you sitting there watching what it's doing and tweaking all the voltages and everything, so it works. Okay, you're good to go. In the real world, that chip you design gets shipped to some who knows where production facility. When they put a cell phone together, that could be sitting in storage in a humid environment, hot environment for a very long time. When they put it together and they're soldering it, or thermally, basically building the part, they could be overheating it. They could be using cheap voltage regulators to power up your chip. So it's a noisy power supply. Your customer may be using it. I don't know why, but they're using it. Oh, that's like another example is, let's say they're shipping it in a plane at however far a plane flies, I don't know, 10,000, 20,000 feet, where it gets really cold, and the part gets really cold in while it's in transfer, or the customer is in Sweden or Finland using it, so it's really cold. So you get the idea. It has to be reliable and work along a whole bunch of systems. So what if it's not reliable? Well, again, the example of a cell phone. If it's not reliable, your customer, the cell phone maker, is going to get a bunch of return parts. People are going to return that cell phone, or they're going to get a lot of calls, a lot of complaints. They're going to get dinged. Their reputation is going to get dinged. And guess what? All that transfers to you. When they get returns on their cell phone, they want the money back for the chips you sold to them. They're not going to use you for the next generation chip, et cetera. So reliability is got a real cost. Okay. Scalability, I'm not going to talk about much, but okay. So the next one is just how fast works. This really goes in how well your device is operating. Okay, that means if you're you're using example of a cell phone chip. If your chip is 10% slower than your competitor's chip, means that, I don't know, your camera turns on later. It's annoying to use as you're scrolling. All this delays and stuff add up. So just speed and operating frequency is another big figure of merit. Okay. And lastly, we're going to talk about, again, power dissipation or energy to do something. Energy sort of comes down to, you're sort of draining your battery, same with power. And, we talked a little bit about that. Power consumption, the higher the power consumption, the more expensive it is to cool that device. If you're going to put liquid cooling, if your system needs liquid cooling compared to your competitor that needs only air cooling, well, your system is going to cost a lot, whoever's buying the chip from you. So they're not going to buy it from you. They're going to buy it from somebody else. Or, you drain the battery on your cell phone much sooner. Okay. So these are sort of the big four in terms of the deciding if a design how well it works. Cost, how reliable it is, how fast it's running, does that function that you want it to do, and how much power it consumes. Okay, so now let's look at the cost of putting a chip together. Like I mentioned, there's two components. There's this non-recurring engineering costs. Okay, and what's that? We talk about the design of the design team, computer-aided design costs, the mass generation costs, setup costs. So it just shows up once. Okay, and then the recurring costs is how much it costs to build each chip. Okay, so one of the important things about it, so these are the important things, okay, is the bigger the chip area, the more your chip costs, because you are buying a silicon wafer from the factory. Okay, if you can put 1,000 chips on that wafer compared to 100 chips, the design that can cram 1,000 chips in that wafer is going to cost 1/10 per part the cost of the thing that does 100 parts per wafer. Okay, so that's one of the things you see a lot in in silicon, is you want to make your chips as small as possible so you get as many of them as you can on a wafer. Okay, so one is just the number of parts you geometrically can fit into a wafer. As we'll see, because there's another factor, which are defects, manufacturing defects, it even increases that importance even more. So recurring costs means you want to make your chips as small as possible. Okay. The other thing is, again, like anything else in a production environment, if you're buying, a million things from your factory, you can negotiate a better price per unit than if you were buying 1,000. This is the way it works. So if you're in a high volume environment, again, let's say you're designing something for a cell phone, the silicon wafers you get from the factory, you can negotiate a lower price than the DoD, Department of Defense customer who's only buying a few wafers. They're going to get really high prices from the fab. Okay, so those are those two factors. Okay, so first looking at the NRE costs. One of the things that's been happening is that these are just going astronomically up. And so in the horizontal axis here, we have the generation of the silicon process, okay? And on the vertical axis, the NRE costs. And these bar charts are divided, and we'll talk about all the different components that go into this. But using the example of that 820 Qualcomm chip, it was kind of right around here. So that was around, I don't know, 2015. All these processes are still available, but so this is the time that it was sort of the bleeding edge. And you were talking about $100 million. This is a sort of average thing. So it doesn't mean that the 820, the Snapdragon 820 cost that much, but just on the average. Okay, and not like I mentioned, in 2021, my brother is working on at the 5 nanometer process. And you can see just over those 5 years, the difference in cost. Okay. So let's look at this bar chart. Okay. So each one of these bars, there's different components of cost. Okay. So let's say this is the entire cost. This is the entire cost of this semiconductor product. Okay, so remember in the previous slide, in the Snapdragon slide, I showed you all the partners that the chip company needed to help sell their product. It's not just designing the chip. You got to make sure there's software comes with it and so on and so forth. So those all have costs. But if you look at this, is sort of the traditionally seen as just designing the silicon part. Okay, so the actual design, this is another thing that is very different between academia, research environment, or in a production environment. You can see this is sort of the design. This is like sort of the circuit design. This is the layout. That means somehow, the circuits are what you can think of as like in your PSpice or whatever. It's a different set of tools, but you can sort of see as these schematic symbols, right? Transistors, etc. Somehow we'll see how you have to translate those into an actual transistor drawing. So that's the physical. So this, if you were going to design a chip in an academic environment, these two would be your costs, okay? But in a real environment, you spend more on making sure your part works or verification than you even do on the design. That's really eye-opening when it happens to you. because everybody's so focused on design, 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 and nobody includes the cost of the verification. But because these circuits are so complicated, again, you're talking about 2 billion, 20 billion transistor system, you have to make sure you've tested every which way of this thing not working and making sure that it meets the customer specifications. Um, Imagine all the different modes that a cell phone chip runs in, all the different components it interfaces in. So you have to, and it's like a very complicated chip. So just to even set up your simulation takes a long time. So anyway, so those are the things that go into your actual design. And again, in an academic environment, that's where you stop. But in a real environment, there's stuff you have to do after you get your silicon back. You have to put together a bunch of software so your silicon becomes usable by your customers. And you have to build a bunch of prototypes and make sure they work in a real cell phone, in the case of a cell phone, etc. Anyway, so these are the sort of the takeaways from this slide, is that the cost to design a chip has been going up tremendously. So, I talked about last time about how this is going back to the golden days of design, meaning that now a lot of people are working on ways to reduce these NRE costs by using things like this RISC-V architecture, and there are a bunch of other activities going on to try to reduce this cost. Now, does Qualcomm care if it's $500 million to design a chip? They want to contain their costs too, but remember, these guys sell hundreds and millions of this thing that they probably sell 500 million of these chips. So this NRE cost doesn't hurt them as much. But if you were gonna, sell even a million of these parts, even a million of these parts, just if you amortize this cost, it's, what is this, $540 just the amortized cost of your design, before you even include the cost of the silicon of the part that you're selling and the testing and all that stuff. Okay, so that depends on where your market is. It could end up really hurting you or not being as important. You always want to reduce it, no question. Okay, so that was non-recurring engineering costs. Okay, the other cost is the recurring cost. Okay, so this is the cost per chip. And like we mentioned, it's, there's different costs, but big part of the cost is the cost of the silicon. Okay, so I keep forgetting to bring a sample wafer. I'll see if I can remember to go grab one this weekend from the office. But typical silicon wafers are, at this point, really most of them are 12-inch diameter, meaning about yay big. So if I had a wafer in my hand, it would be like the size of, I don't know, medium or a large pizza in diameter. And it would be about a millimeter thick. Okay, so looking at it from the top down, it would look like a circle. And then here's this is all, you've sort of replicate the chip a bunch of times in here. So these are the single die that are printed onto this wafer. And then what you do is you cut out, this is not like a saw that you would have at home. It's all going to be, happening at production facilities. But basically what they do is they cut these parts out put them in a package, test them, and so on. Okay, so but it all starts with the wafer. Okay, and like I mentioned, the cost per transistor is going down, so the number of things you can get into a part are going down, but you still want to make these parts, make the number of die as small as possible. So imagine, again, let's say when you go to a factory, what they say is, okay, if you buy 1,000 of these are called wafers, and that's what the factory cares about. They say, okay, if you buy 1,000, so 1,000 wafers per month, it's going to cost you $2,000 per wafer. And if you buy, I don't know, $10,000 wafers per month, it's going to cost you, I don't know, $1,500 per wafer. So the more wafers you buy, the lower, the cost of the wafers. Okay. Now let's say you were going to make, you could put in your design, you had 1,000 parts per wafer, or you had a bigger design that was only 500 parts per wafer. It was twice the area. Okay, so you do the math, right? Here's going to be $2 per wafer here, $1.50 per die. And this would be $4 per die if you screwed up the design and made it too big, or $3 per die. Okay, so that's like the raw cost of those parts. Okay, so now let's see how that works. Okay, so by the way, this is how many, this number, this number of how many parts you get per wafer is called gross die per wafer. Okay, that means physically you could put that many parts on the wafer. Okay, so you can sit here and count how many of these guys there are on this wafer, and that's your gross die per wafer. Okay, but all those parts aren't guaranteed to work. Okay, you could end up, if you notice, there are these things that only partially print because this thing is a circle, not a square, for various reasons. The wafer is a circle, so you get all this dead area. Okay, so that reduces the number of usable die per wafer you have. Additionally, because of defects, okay, I mean, these fabrication facilities that they make these wafers in are extremely clean. Okay, they talk about 1 particle per cubic meter. I mean, it's like vacuum, very tight, but there's still defects. Okay, there are still defects. There are defects that show up in your wafer. There's defects in the very pure gases thereby. There's like dirt in the equipment. Not a lot. It's probably the cleanest thing made by mankind, but there's enough that statistically, you're going to lose parts you know, you'll have a defect that lands on this guy, kills this dude. Defect that lands over here, kills that guy. So not all those gross die per wafer can turn into product. So the percentage of parts that are good and can become a product, that's called the yield. Okay, so the definition of yield is this number of good chips per wafer over the total number of chips per wafer times 100%. Okay, so that means if your yield would be 75%, if 25% of your die in the wafer would be bad. Okay, so that's a definition of yield, and you're going to have to use that. So we didn't look at yield when we figured out this cost. We just assumed every part we had on the wafer worked. But in reality, that's not the case. You also have to see how many parts work, what your yield is in that wafer, and multiplied by the number of dies per wafer to figure out your silicon cost or die cost. Okay. So you've got these components. You've got the wafer cost. This is like, negotiate with factory, build higher volume, increase your volume, increase sales volume, I guess what I want to look at. These are the ways to reduce your wafer cost. Okay. Dies per wafer is you make your chip small. Okay, and we'll look at die yield in a second. Okay, so look at the dies per wafer. Like I mentioned, you have this sort of central part of, oops, sorry guys. You have the central part of the wafer. Okay, that's fine, where you get usable die to start with. And then you have all this periphery where you like this thing ends up being junk. This is probably junk. This is junk. This is junk, bad, 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 bad. So you can't just do, if you want to figure out your gross die per wafer, you can't just say, well, the wafer area is, pi r squared, where r is, I don't know, 6 inches, and my divide by die area. You can't do that. You also have to think about how much you lose on this periphery. Okay, and it turns out that the smaller your periphery, the smaller your die, okay, the smaller your die, the less, just geometrically, the less die you lose, the less area you lose on the periphery as well. So look at this example is kind of extreme example where, for a large die, given the same wafer size, you lose all this silicon area is not used. But, if you're going to use a smaller die, this would be the area that's not used. Okay, so right off the bat, geometrically, and you can see the difference in area between the red and the green. Okay, so just geometrically, the smaller your chip, also the less wasted space you get on the wafer. And there's an estimate of that. So this is the, assuming you use the entire die area, but then you got to subtract. This is kind of rule of thumb about this peripheral area, but it ends up being a function of the die area. So the smaller your die, not only can you get more on the chip, but you use the area of the, sorry, you get more on the wafer, but you also use your wafer area, available wafer area more efficiently. Okay, so again, you have even the dies per wafer. If you make your chip smaller, you win doubly. More die per wafer plus more efficient use of the wafer area. Okay, now let's talk about defects. Let's say these defects were randomly placed on the chip. Okay, so these are the defective parts, sorry, on the wafer. So these are the defective parts of the wafer. And by the way, let me just highlight them all in green. Okay, so these are random per wafer. But let's say what's going on? What? Okay, never mind. I was trying to be clever here. But let's say, you saw two cases where you had the defects were exactly in the same location, same number of defects, same locations on wafers. So this is a hypothetical case. And one wafer had smaller die than the other wafer. Okay. So now let's look at this thing. You can see that because you have large die, those defects are a lot more devastating to a large die. Here, you could put 4 die on your wafer, and the defects knocked out 3 of them. That means, in this case, the yield's only 25%. Okay. In this case, you get, I'm not going to count it, but it's like probably, more like yield is 75%. And this is like a much, much worse of a situation because typically because of the way these defects and stuff work your yield is a lot more dependent on your die area. Okay. I'm sorry, guys. I don't know if you hear that squeaky noise in the background. It's my dog playing with her squeaky toys. Okay, I might have to go out there and take it away from her in a bit. But okay, so all in all, the upshot is that your die cost, okay, guys, it's driving me crazy. Sorry, let me go, and I hate to do this to my dog, but gotta go take that squeaky toy away. So I'll be right back. Okay, sorry, guys. At least she's not barking. She might start doing that in a second. So sorry about that. But anyway, so what ends up being is that once you look at how many you can put on the wafer, this peripheral usage, and the yield, you end up with this really amazing endpoint, which is your die cost is sort of a, to the fourth power of your function of the fourth power of your chip area. So it is incredibly, incredibly important from a recurring cost standpoint for your chip size to be small. So when you're designing a chip, you'll see a huge amount of emphasis in making all the individual circuits, all the individual blocks, the floor planning of the chip, everything is incredibly important to try to cram, make that die area as small as possible. Okay. Okay. Any questions about that, guys? So that's the cost metric. There's other stuff that goes into the cost, but from a, there's like testing of the part, packaging, etc. But from a chip designer point of view, it's all about the area. Okay. Okay. So that was sort of the important thing one, which was cost. Second thing is reliability. Okay, so why would a circuit be unreliable? Well, like why wouldn't it work correctly? Why would it functionally not work? Well, it turns out that noise basically is what keeps your circuit from working properly. I don't know if you guys are, the students in the class that are computer engineers, I don't know, they may have played around with FPGAs. Anybody played with an FPGA or taken a class with an FPGA?
Yeah, I've used FPGAs before.
Okay.
Yep.
Ms. Connor. So let's say if you take an FPGA, because it's like a pretty dense thing, that's pretty noisy. Usually the power supply for an FPGA might be 1.8 volt, 1.2 volt, 3.3 volt, whatever it is. If you actually take a scope, so let's say you think if I had my scope probe and probed my power supply, it's going to look like this. It's not going to look like that. What it looks like is this. And this might be like, it'll amaze you how anything freaking works, anything electronic. This might be 2 to 500 millivolts of noise on your power supply or on your ground. Your digital system is incredibly noisy. The power supplies are jumping around. There's a lot of high frequency signals going back and forth. So the other thing you can do is just take your scope probe and connect the ground to the tip of your probe, that makes it into a receiver antenna, and just let it hover over your FPGA or over your chip. You'll see how huge of a signal you're going to pick up, just electromagnetic emission from your chip. And this is the stuff that's already passed FCC regulations, et cetera. God forbid if you don't pass that, like what kind of stuff you'll be generating. So there's a huge amount of electromagnetic noise in the environment. There's noise on your power supply. There's noise, if you imagine if you have 20 billion transistors on a chip, all these things are like, they have connections between them, running next to each other, etc. So these lines also all can couple to each other, capacitively couple to each other. So there's a lot of noise in the system, a lot of electrical noise. You think of the digital system as like being like noise free. In fact, I just got through telling my microelectronics class that digital is good because it's noise free, but it's really only noise free as long as your logic is good at rejecting noise. Okay, so this is the second thing. And where does that rejection work? Okay, so this plot is a plot of the transfer function of an inverter. Okay, so inverter has an input and an output. And if an input is 0, the output is a 1. And if the input is a 1, the output's a 0. Okay. In practice, in the real world, you assign a voltage value. So logic 0 is usually voltage 0. and logic 1 is whatever's your power supply. I don't know, 1.8 volts, say, or 1.2 volts, whatever's your power supply. Okay, in reality. Okay, so this plot here is the transfer function of input versus output. Okay, so when the input is low, your output is high. Low input, high output. And when the input is high, your output is low. Okay, so this transfer function is something we'll look at over and over again because the inverter is for a logic family. So we're looking at almost exclusively at the CMOS of static CMOS logic family. We'll analyze the hell out of that. Basically, we'll look at this the inverter is like an example, is a sort of simplest example of what how a family works. So it basically looks like something like that. Okay, so that's the transfer function. But the real logic family, if you had a perfect digital circuit, it would kind of look like the transfer function would look like, whoops, do that badly. Transfer function would look like that. And we'll see why that is. That gives you the most rejection of noise. Okay, you would have an extremely sharp and abrupt edge right at the middle of, oh, I'm sorry, I drew this badly. So what it would look like is come here and you would use the entire available supply range. Okay, so that would give you the best transfer function, the most efficient, the most noise rejecting transfer function. Okay, so we'll look at what gives you a good transfer function and how what the definitions of these transfer function mean, what are the permissible ranges for a logic high, what are the definitions and permissible regions for logic low, and what makes a good inverter or a logic family to have as much noise rejection as possible. At this point of transfer function, it's all about noise rejection. Okay, so we'll talk about that. We'll talk about the noise margins when the time comes. We'll get more into details. So those are noise margins. And then from the system standpoint, usually you're not talking about noise margins. You talk about the noise budget. So your circuits have a certain, because of the way you designed them, they have a certain noise margin, they have a certain power supply, and the way that at the chip design level you look at it is, okay, I can afford to have this much noise on my supply lines, ground lines, whatever, to make sure I have a noise-free and reliable chip. Okay. So the main important point of a logic family from a reliability standpoint is how well you're able to suppress all this noise that it's in your real environment, which is a very noisy environment. And when we talked about reliability, we also talked about temperature and low temperature, high temperature, all that stuff. That affects, as you'll see, it'll affect the noise margin of your logic family because you're dealing with transistors that change their performance depending on what temperature they're at. Okay. And another important thing about logic families is the way the transfer function looks, because it's very important to have this regenerative property, meaning that if you have two inverters following each other, let's say you had a noisy input here. So if I draw that input, so if this was time and this was voltage, okay. So that input here, 1, 2, 3. Let's say that input had gotten really mangled. So it was a very low voltage swing input for whatever reason. Okay. If you have a regenerative property for if your transfer function looks like a certain way, like we'll talk about, what happens so this is node 1, node 2 will look like, it'll help clean things up. And by the time this is node 2, by the time you're in node 3, you are at your nice full logic swings. Okay, this is called a regenerative property. So you're regenerating a good signal at every layer. Now, let's say the opposite was going to happen. Let's say at each point here, each one of these guys, each one of these inverters was going to screw up your signal more. That means if you start putting these logic, and that's the way logic works, combinational logic, you have inverter going to a NAND gate, you have a lot of layers of logic, lots and lots of layers of logic. By the time you get a few layers in, there won't be any signal left. So this has to have a certain look to this transfer function. Okay, so that's important. So this is an example of what this regenerative, sort of what I just drew. Okay. The other important thing, I'm not going to talk about it right here, but you have to be able to drive lots of gates like yourself. Okay, so actually this is probably a good place to stop. So again, we talked about logic has to have a certain transfer function, like this V input, V output, to suppress noise. So on Tuesday, we're going to talk about why this is the ideal shape for that. And then we'll talk about how some older logic families didn't have that shape, and how CMOS technology is very close to that shape. So it's a good noise suppressing logic family. And then we'll talk about how you can optimize it to suppress as much noise as possible. Okay, guys, any questions? Okay, if not, have a good weekend. And I will talk to you guys on Tuesday. Take care.
Thanks, Professor.
Thank you, Professor.
Thank you, Professor.
Bye-bye.
Professor. Have a good one, Professor.
Take care.